I know this is alpha in that corner. Normal force is coming down like this. So all I need to do is figure out sort of the relative angles. Normal force is going in that direction. And I need to figure out how much of it is down and how much of it is to the left. Lloyd?
So you can assume that the normal force goes like
Louder,
bisects-
please.
You can assume that the normal force, I guess, bisects the right angle of the bottom way.
You can't assume that it's bisected. Bisected, you always picture as two equal parts. I just started up again. Okay. All I'm doing is looking at angles here, so it really doesn't matter where this one, whether I go through this corner or not. It's just simpler if I go through the corner from a geometry point of view. I feel like I didn't quite address your comment, Roy.
No, I think you did.
Did it? Okay. So if that's alpha, I know this is a right angle because normal force, well, normal is perpendicular. So that's a right angle there. So I've got a right triangle here, so this angle here must be the complement to alpha, which I'll just label as alpha prime. And then I've got a right triangle here, because weight is acting straight down. So this angle here must be alpha. So if I look at my normal force is coming down like that. I'm breaking it into components. This angle here is alpha. So this must be y2 sine of alpha, y2 cosine of alpha. Because that makes sense, Cooper?
Yeah.
Okay. Other questions up to here? All right, once we've broken it up into components, now it's the equations of motion. So we're just basically at this point, we established our convention over there. So the I hat equation, take all the ones that are positive, add them, subtract the ones in the negative direction, is equal to mass times acceleration. That's going to that way, minus y2 sine alpha minus fr is equal to mR. And then vertically, there's no acceleration. So I have only one thing that's going up, and then going down, I got these three things. And done.
Isn't it supposed to be plus F2 cosine alpha?
Here?
Yes.
Yes, it should. Thank you. Probably the biggest mistake that I see for people who understand what's going on about how to approach the problem is getting the angle. Like I messed up here where I wrote down theta just out of habit. Also, I noticed this on one of the master sets. There was an alpha. Alpha basically, as one student put it, the Jesus fish. That's the letter A, that's an alpha. Now, there's that gray area of, it looked kind of like something like that. I'm going, that's close, sorry. But acceleration, if you're doing that for alpha, acceleration better not look like the same letter A. So it's better if you do the alpha more like that. But I know that when it prints, the Times New Roman Greek version, it doesn't quite look like as much a fish as that one does. So just be careful about what's given and what you use. if I did it correctly, and I try to do this on the ones where these, actually for all three of them, if you actually took the forces that I put here and you added them together, the net force here should be pointing that way. And since these are not accelerating, if you add those up by taking the actual length that I have right there and you move them around, it should add up to 0. The forces basically end up back where you started. I know I did it on the later test. The early test when I started doing these type problems, less careful. So I think on this one, I drew it correctly. Questions?
So why, is there acceleration in the problem? Why is that written?
Except these are not accelerating based upon the way I worded it. I think the first time I used these shapes here, it was find the equations of motion of all three objects, and then by this time I realized that was overkill. Other questions? And I feel like I did very similar to that class. And force diagram problems, people did reasonably well in the master set. So. Any questions before I shift gears and start talking about energy?
Talking about kinetic energy?
And potential.
Okay, so are we gonna do number 6?
Okay, we can. I was gonna skip over it, but if you would like, we can do number 6. You'll notice there seem to be gaps here, and that's because when I did the diagram, I used too faint a line that the printer just didn't pick up.
Oh, they were supposed to be boxes.
I apologize. What was?
Those are supposed to be boxes.
Yeah, there's supposed to be boxes, and then there's supposed to be a pulley at the top. I think once again, I went with alpha and beta. All right, so it starts out as frictionless and it is in equilibrium. Static equilibrium. And the question is, what is beta? I believe I gave you M1, M2, and alpha. What do I give you? Mass 1 is twice mass 2. And alpha is, I think I had 25 degrees. Yep. Rope and pulley are ideal, so we don't have to worry about friction from those. Rope is parallel to the ramp and connected at the masses, and it takes place on Earth. So we know what G is. As with so many problems, force diagram. I really only care about mass 1 and mass 2. Weight 1 down, weight 2. And these really should be subscripts. I notice some people when they draw it, the weight 2 like that, that's actually W squared, so it should be a subscript. There's tension. There's tension. I know that the tensions, because it's an ideal rope and pulley, the tensions are equal. I don't need different subscripts there. There's no friction, there's no other. Only other thing is normal force. Got Y1, Y2. All right. It's an equilibrium, so there's no direction of acceleration here. So pick one. We have to set up a coordinate system. And it's just a little bit simpler if we sort of imagine a direction of acceleration. And arbitrarily, I'm going to choose that way. I1, J1. I2, J2. So what do we need to break up? What are we decomposing?
2/8.
Yep. And so for mass 1 here, I have tension acting up. I have normal force acting this way. Breaking weight up, we've done it several times before, as well as in the videos. This will end up being W1 cosine of alpha, W1 sine of alpha. And for mass 2, got Y2 tension, we have 1 there. And then W2 sine of beta, W2 cosine of beta. How many equations of motion will there be?
2,
4.
4. Yes, I see.
Okay. Let's go with 4. All right. Give me one of them.
FT, W1 cosine alpha plus 1, or,
That's in a different direction.
I'm not sure.
Equals mass times 0.
We've done all the forces in that direction, so it's equal to mass times 0, because it's an equilibrium. All right, 1 down, 3 to go.
FT, minus W1 sine alpha,
This one that you just did.
cosine, sorry.
All right, let's start again. All right, so we did that one.
Oh, so it'd be Y1 minus W1 cosine alpha equals mass times 0.
Okay, 2 down, 2 to go.
So the other one would be Y2 minus W2 cosine B equals mass times 0. And then the other one would be FT minus W2 sine B,
Beta.
beta, sorry.
Go on.
FT,
Equals.
mass times 0.
Yeah. All right. The reason why I hesitated there is I established that down the ramp was positive here. So even though, because it's equal to 0, it's not going to matter if you Kristen wrote down what you just said. It is a correct statement. However, I am going to stick to the convention because it potentially is going to be helpful a little bit later on.
And this is for question A, right?
This is for A, yes. So we had W2 sine beta minus ft is equal to 0. All right. We're trying to find beta. Because there's no friction, the two normal force equations have no impact in our particular problem here, because they're both perpendicular to any possible movement. If I just add these two equations together, another advantage of setting up this, using the system I set up there, if I add them together, the tensions are going to cancel out. If you'd rather solve for tension and then plug in, sure, why not? But I'm just going to add them together. I get a positive tension and negative tension, those go away. I'm left with W2 sine beta minus W1 sine alpha equals 0, or M2G sine beta equals M1G sine alpha. G cancels out, so it really doesn't matter what planet it's on. Whichever one it was. So we assign there. So sine of beta is equal to M1 over M2 times the sine of alpha. I don't know what M1 and M2 are, but I do know the ratio. I know that mass 1 is twice mass 2. So this becomes 2 sine of 25 degrees. Whatever that happens to be. Like 35 degrees. Beta is 58 degrees. There. Ah. And that's the answer to A. So, questions up here?
We were supposed to retake the arc sine at the end, right?
Say it again?
We would take the arc sine at the end after we solve for
Correct.
G sine.
Correct. All right, so now if we assume that they start at rest, if beta is cut in half, so whatever we had before, so for part B, beta for part B is half of that, so 29 degrees. What's the acceleration? Now we still have a frictionless system here. If beta is cut in half, which way are these things going to move?
Down to the right.
That way? No, that way.
Yeah.
How do you get that? How do you reason that out? That phone's really made our lives better.
No, never mind. Do the other one.
Yeah, if this becomes less steep, then this is gonna have more of a pull on it. Recognize we got this W2 sine beta going this way. If beta becomes smaller, then that becomes smaller. All right, so it's gonna go the other way. We could still solve it with this convention right here, or we could flip the eyes around. I'm gonna say let's flip the eyes around, but if you solved it like this, you should expect your acceleration to be negative. And that just means it's going the other way. So the only thing that's really changing on our equations over here, if I flip my convention, for stunning effects there, so that is now flip I2 this way. So now we're solving for A. Again, there's no friction involved, so these two equations aren't going to have any impact right now. And probably should actually go to something like that. And I'm going to go through the exact same process. I'm going to add these two equations together. And I get W1 sine alpha minus W2 sine beta is equal to M1A plus M2A. I know alpha and beta, I can find the weights easily enough. That's just M1G. Actually, M1G sine alpha minus M2G sine beta is equal to M1 plus M2 times A. So my acceleration will be this whole thing, M1G sine alpha minus M2G sine beta divided by total mass. And now it's a plug and chug.
This is for B.
This is for B.